Okay, this is a just a quick video I'm putting together to go over the tech talk I gave this past Wednesday at the club meeting. And what it is, it's a construction, a test update of the 5-band auto-link dipole antenna I've been working on and have reviewed with you guys the past few meetings. I'm putting this video online with a password because I kind of like to keep this confidential. I think based on my research, I haven't seen anything quite like it, and I kind of want to approach maybe some antenna manufacturers with the results I expect to get and see if we can do a little business. And don't want to give away the solution because I think once you see it, it's pretty obvious what it is and how it works. So if you can kind of keep it quiet, I'd appreciate it. But welcome you to play around with it, and if you want to get started on one, let me know and I'll help out. The other thing on this, at this stage of the development, I think it's a real good example of how you go from knowing something to understanding it. And this is a big part of engineering that I've found, where in engineering school you're taught a lot of things and you know them, but you really don't start understanding them until you actually start working with it. And this is a good example of that. So with that, we'll go on and get started. If you look at multi-band dipole antennas, there's two basic designs that you'll find. The first one's what's called a fan dipole, and the way it works is that if this is the feed line back to your transceiver, you build several different frequency dipoles. For example, this one here, these elements here are the 80-meter dipole, and then the guy built a 40-meter dipole and a 20-meter dipole and a 10-meter dipole, and then kind of mechanically linked them together with some sort of standoffs, and then that's what is elevated into the tree or the mast, or however you're getting it up into the air. And one of the things in my research I was never able to get a good read on was tuning these dipoles. And the way you tune a dipole, say if you had a single frequency dipole, is you'd start off with some estimated dipole length. You measure the resonant frequency, and then if you're above or below the resonant frequency, then you start trimming the ends of the dipoles, making the dipoles shorter to raise that resonant frequency. And in the literature that I read, that's basically the same approach people would take, and they would start at the high frequency or the lowest frequency, tune that dipole, then they'd go to the next one and tune that, and the next one and tune that by trimming the ends with an antenna analyzer reading. But it seemed like everybody had a similar situation where if they had more than just a couple dipoles, there was some interaction between the dipoles as you trimmed the higher frequency elements. And you can see where that would make some sense, because all of the elements on one side of the dipole are connected together, and all the elements here on the other side are connected together. So let's say you got the 80-meter tuned, and then you go down and you start trimming on the 40-meter. You're going to change the equivalent circuit of the dipole, and it'll change the inductive values and the capacity values of the dipole, which have to impact the inductive and capacity values of the dipole that you just trimmed. So when you adjust this one, it's got to have some impact on this one, and the same with the third one you might try to adjust, and then the fourth one. And nobody really came out to say specifically how they approach that problem, other than saying, well, they eventually got something that worked. And that didn't give me enough confidence to start building a fan dipole, but I thought it was an interesting concept. The other approach to a multi-band dipole is to design it as what's called a linked dipole. And the way that works is you say, in this case, they're making a 4-band 20 to 80 meter dipole. And the first dipole that they make up here is the short one. In this case, it'd be 20 meters. And then they would open up the wire and put a jumper in here that would go to the next link. So that what you would want to do is, say if you're at 20 meters with no jumper here tying this wire to this wire, and you want to go to 40 meters, you have to lower the dipole, and they're usually deployed as an inverted V. You have to lower the center point of the dipole, install a jumper in here, which could be just anything from alligator clip wires to wired and bolted jumpers to tie this wire to this wire, so that your overall length of the antenna is this length here, which would give you the next band up, which in this case would be 30 meters. And then likewise for going to the next frequency band, you'd have to insert another link here, each time lowering the center point of the dipole, inserting the links, and then running it back up. So that is a fairly typical way of doing multi-band antenna, especially if you get into QRP. I've seen a lot of them for QRP, which is the low power, and you have pretty small gauge wire here, so it's not too difficult to manipulate things. So both of these designs can give you a multi-band dipole, but they aren't without some trade-offs. So what I got to thinking is that in order to address those problems, to where in the fan dipole all of the elements are interconnected, and on the link dipole you have to constantly lower and raise the thing and insert links, I thought, well, what if we took a dipole antenna and start off with what I call the Z element. This would be the first one. If I had just 2 wires, I could trim these lengths to get the resonant frequency where I wanted it to be for my targeted band. So let's say in the case of the way this antenna is designed, I started off with these Z links, these Z elements for 6 meters. So I said, okay, let's make this a 6-meter dipole. And then rather than connecting them all the other elements together like we do in a fan dipole, or having to put links between the elements to jumper them together, what if we use a remote controlled relay? And or in this case there would be 4 relays where I could turn on any of these contacts at one time, making the total length of the element here. For example, if I close the A contact, that would be the total length of the antenna, and then I could adjust this element to get the desired resonant frequency. Let's say if I've got my Z at 6 meters and then I want this A to be at 10 meters, I would trim the lengths of the A element on both sides with this contact closed to get me 10 meters. Then I would open this link, and then I would close the link on B and tune each side here to the next band, which in this case for this design is 12 meters, and then do the same thing for this would be 15 and then 17 meters. So what that would do is that would solve the problem of the fan dipole having all the elements connected and having interaction between the inductance and capacitance of each element, and then it solves the problem of the link diode or link dipole, that rather than having to lower the antenna to put jumpers in, I just use a remote controlled relay to close this contact and make the total length of the element this length, the A plus Z length. And then you would come down here as you normally would with a dipole with a coax and go to your transceiver. So that's the basic idea of what I call an auto-link dipole. And theoretically you could do 6, 7, 8 bands if you found relays or had relays, remote controlled relays that could give you that many. And each one would be electrically isolated, because when you're selecting one band, only one element is attached at a time, and these other elements you're not going to have interaction with like you do in the fan dipole. So in order to mount something like this, I knew, since I was going from 6 meters to 17 meters, the overall length of the 17 meter dipole was going to be under 15 feet, or the element's going to be under 15 feet. So I came up with a PVC pipe design where I started here in the center, and I had two center points. One was a Y for an arched mast, and I'll show you a picture of that, or I could use a T in the center, a horizontal T, so I'd have a flat mast that I can mount the antenna on. And then that was set up so that I could mount this PVC antenna mast on top of a alpha antenna as a tripod that I already have used for the alpha antenna's hex antenna. We also use the same tripod for the alpha antenna's FMJ 10 to 80 meter vertical antenna. So this was readily available. Very good tripod, very sturdy. It's really done a nice job for us. So this is a picture of the arched mast that I put together, and you can see there's a Y connector here, a PVC Y, and that was a little hard to find. That's not a real common configuration. But then the way I did the mast is I've got a 5-foot section, a 1-inch pipe here, PVC schedule 40 with the screw-in adapter at this point, and then I had a 1-inch to 3/4 inch pipe screw-in adapter here where I would put a 3/4 inch PVC pipe, and then another 1/2 inch to 3/4 inch adapter here where I would attach the final 5-foot section of 1/2 inch PVC pipe. So that gave me a good symmetric arched curve that I could mount the antenna that I was going to build to that. And the way I mounted it, just for testing, I'm using some Velcro cable ties and just attach it to the mast, and that's worked out pretty well at this point. So this is a close-up of the RF generated or controlled 4 relay module, and it's about 2 by 4 inches. Bought it on Amazon, about $18 each. And this is the circuit board inside the box. I didn't use the box, it was pretty small, so I put it in a larger watertight box. And things to note, the board has 4 relays on it. I labeled them here A, B, C, and D. This is an antenna for the key fob that will control the relays and turn them on and off. And you stretch this antenna out over the circuit board so it has a good reception of the signal from the key fob. There's a jumper right here that you have to change, and there's 3 different settings depending on what you want this module to do. And what I wanted this module to do is that when I hit the D button, only this relay closes and all the other ones are open. Then if I hit B, B closes and all the other ones are open. So that was necessary to set this jumper in the interlock position. There's a program switch here that you use to program the key fob that you're using to the board. And the way that works is you press this button one time, the LED light starts going, flashing, and then you press, say, start off with the A button, and then the LED light goes off, and then you press this button again, and you then press the B button on the key fob, and then do the same thing for C and D, and then that tunes the key fob to the module, so that when you hit C, this closes and all the other ones remain open. You bring in 12 volts DC here to power the module, and there's a couple different ways of doing it for the prototype and the portable operation. I'm just using a 12 volt rechargeable battery to supply the power to the module. And then down here are the connections to the relays, where the connection from A to B is a normally open contact and B to C is normally closed. And the way that's done is with this single pole double throw relay here. You can see that with no power on the coil, this side of the relay is closed, the switch is closed, and then when you energize the coil, the little arm here moves to this other contact, and then that side's closed. So this is the normally open contact right here. So when you energize it, it closes, and that's right here. This closes between A and B when this relay is turned on. So anytime you connect, push the button for one of these relays to energize, then this set of contacts closes, which is what we're using in the antenna to connect the Z element to, say, the A element or the B element. And I think that's about all to point out to on this one. Okay, this is a look at how the relay module is wired and installed into this waterproof box. What I did is I took some of these Velcro strips, two-sided Velcro strips, and mounted the board on the inside of the cover for the waterproof box. And this cable here contains the A, B, C, and D elements. It's the 4 conductors. This cable here contains the Z element, the one coming from the center of the diode. And you can see what I did is I took the Z element to here, and then I jumpered it to the center post of the next relay, which would be this point right here, B. So you can see I've got the B's all jumpered together here so that they all have the same common point, which is the Z element, so that when these contacts close, when this AB here closes, then the red wire is connected to this black wire. Here, this black wire is connected to that black wire. When I do the next one, the white wire is connected, and then the last one, the green wire is connected to the Z element. So that's the main information for this, but it's just wired at just like the diagram shown. One note, I cut the edges off the mounting holes of the circuit board, making sure there were no traces underneath there, copper traces, so that this would fit, the circuit board would fit inside the lid of the box. And then when this closes up, the screws gives me a good watertight seal around here, and everything fits pretty nicely. Okay, this is just a closer look at the interconnection diagram. You can see this red, green, white, and black wire are the A, B, C, and D elements, and this is how they go into the terminal strip. And then the Z element is this one coming in here, and then it's jumpered to the other center post of the 4 relays, so that these all the B connections are jumper together and form the Z element. And then your 12 volts DC comes in here, and it's clearly marked on the circuit board the positive and negative polarity. So that's just kind of a zoom in view of how the circuit board's wired. Then I had to get into some testing. What I wanted to do was to make sure that the relays responded the way I thought they were intended when I click the key fob here. This is a little key fob that has A, B, C, and D buttons on it. So I used an ohm meter and a jumper here in the center, so that I would put one side of the ohm meter, sound the black lead here, and then the red lead of the ohm meter to the black lead here, and then I'd close the black button, which I think was C, to make sure that I had continuity through all this so that the relays were working. Now this was a critical step because I did find one of these relays had a failure in it, in that when I closed, say for example, the A button, I'd get the A contact closed in one of the others. The other relay performed as expected, where when I closed one button, only the right relay contact would close. So this is an important step to shake down that you've got the modules, relay modules working properly. Okay, so at this point I still had some concerns and unknowns. One thing that I'm doing, I was hoping I could get away with, I didn't know if it would work or not, was that I knew that the elements, the red, white, green, and black wires, were wound together in a bundle. And I know that that winding of the wires introduced capacitance and inductance into that cable. But in all the research I did, I couldn't find any way to really quantify that capacitance and inductance that was introduced. I knew it was there, I just couldn't figure out how much. And if I could have figured out how much, then I could have gone through an analysis by analyzing the added inductance and capacitance to this circuit here. And what this is an equivalent circuit of a dipole antenna, where you have a series capacitor and inductor, and then a parallel capacitor, resistor, and inductor, and that models what the transceiver sees in when it's connected to the antenna lines here, A and B. So if I had known what the added capacitance and inductance would have been by twisting those wires, I would have been able to analyze this circuit as a function of frequency and tell me what it would do to my SWR and my reactance at different frequencies. But since I couldn't get that information, then that means that I had to build it and test it and see whether the impact of the added inductance and capacitance was going to be significant or not. And that's what I'm talking about, going the difference between knowledge and understanding. You really, just because you have the knowledge that something's going to happen, you may not be able to get everything nailed down to the point of understanding it, and that's why you have to build these things. And that's why a lot of engineering involves, particularly on new design, building models and building prototypes to see how things work out, because you just don't know everything you need to know. So that was a concern there. What does that sheath effect of the winding of those wires together going to do to me? And then the other thing that I wasn't able to nail down in terms of numbers, but I knew it was an effect, was the velocity factor of wires. And in this case, the wound cable that I had, the cable that was in the sheath, was 20 gauge wire, which is fairly small wire, but not the smallest you can get by any stretch. And there is an impact on the gauge of the wire on this antenna constant. That this is a formula that's generally used for computing the length of a dipole antenna. And I think the first time we saw this was in the technician study guide, where you take 492 and divide it by the frequency that you want in megahertz. And say if you're wanting 7.5 megahertz, and you take 492 divided by 7.5, and that'll give you the length of the antenna in feet. Now, if the velocity factor changes, then this antenna constant, this arbitrary, it's not arbitrary, but it's a kind of a general solution, the 492 will change. But I didn't know how much it would change. So there again, it was one of those unknowns that I was going to have to find out what it might do to me through building a prototype. So what I did is I put that antenna together and I mounted it on the mast, and I wanted to check the Z element, and this was the SWR plot up here. Tells you up here in the corner what the plot is. This is the SWR on the Z element, and determined that the resonant frequency was 19.3 megahertz, which is right here. I was shooting, actually I'd be shooting up here into the 6 meter range, and then what I saw is I've got this primary resonance frequency here, and then normally what you see in an SWR chart is that it starts up here at a high SWR, and as you get close to the resonant frequency it'll come down to some minimum SWR, and then it'll go back up. Well, I have kind of a bizarre curve here in that I've got a real sharp, narrow resonant band here in the SWR, right around 19.03 megahertz, and then it comes up, and then I've got a dip here, and another dip here, and another dip here, and these dips are caused by the change in reactance going from capacitive to inductive. So this is telling me that I do have a considerable amount of additional inductance and capacitance in that bundle. So the bundle is causing me a problem, and I'm not going to be able to use it, even though I thought it'd be pretty slick if we could do this antenna with just one cable and all the multi-conductors inside the cable. So this is telling me, nope, you're not going to be able to do that. So that was something learned. I understand that a little bit better now. Then, so what I decided to do is I separated the wires out of the cables, and I repeated the 6 meter test. And separate the wires, all I did was I took an X-Acto knife and just cut a score mark along that gray cable, and pulled the wires out and spread them out so they wouldn't be wound around each other like they were when the cable was built. Okay, so when we take a look at the results of the 6 element test, or 6 meter element test before the trim, we started with a 59-inch long element length, and you can see we've got that asymmetric standing wave ratio plot that isn't what we'd like to see. Then if we take a look after we trim it, trying to move the resonant frequency up, we took 16 inches off the element length, left us with 43 inches long. You can see it's still asymmetric, but it's flopped a little bit in that it's different than it was here before we trimmed it, and the standing wave ratio is going up. And then if we take a look at trimming it again, trying to hit that resonant frequency, had to take another 20 inches off, leaving it 23 inches long. When we started at almost 5 feet at 59 inches, we can see that we're still kind of asymmetric in that shape, and the standing wave ratio increased even more. So that's telling us something's not quite right here. So step back and kind of take a look at it. It's summary, the shape of the SWR curves aren't typical the way we'd like to see them. The resonant frequency changes didn't respond as expected. Uh, we probably should have ended up in this position here with a length, say around 4 feet 8 inches, which would have been the calculated value, but yet we're down here under 2 feet. So that's kind of screwy. Um, and then um, that would tell us that the antenna constant that we used in the initial calculations for the length of these elements was not close to what this antenna actually is. So something is pretty screwy, and we can pretty much uh, best guess would be that the wire gauge of the antennas is what's getting us here, because that would definitely change the smaller wire. Um, Velocity factor would be lower than the larger wire velocity factor, and this is the type of result we would expect to receive. So the 20 gauge wire doesn't appear to be acceptable for this antenna design. Okay, now the next step, what I wanted to do was take a look at the A, B, C, or D elements and see what the um, cable might do to that with the other wires being wrapped around it. So this is a look at 17 meters, which is the D element. Uh, Ran a frequency sweep to get the standing wave ratio. You can see we've got the asymmetric uh, SWR curve, got a little bit of jaggedness here, which might be an indication of that capacitance and inductance that we saw on the 6-meter element. I think one reason it may not be quite as aggravated here is that we're at a lower frequency, so the reactances would be lower, and that may be why it's just an indication of some issues there. Any way you look at it, this isn't a good trace, and need to think about that a little bit. So the conclusions that I come to from after looking at all this information is that both the bundled cable and the wire gauge give us adverse impacts on the antenna performance. So our next step would be to use single strand 12 gauge wire, and I want to use the same wire that we use in our base station dipole antennas. It's a 12 gauge finely stranded and built just for antenna applications. So we'll see what that does for us. So what I did is I replaced the 20 gauge wire for the 6-meter elements with the 12 gauge finely stranded wire, tuned the antenna for the target resonant frequency of 50.125 megahertz, and this is the part of the 6-meter band that's used for single sideband communications, which is what we'll be using this antenna for. You can see the calculated length I came up with was 4 feet 8 inches. After tuning, I'm at 4 feet 4 inches of wire, so that's pretty close. That's looking good. You look at the SWR plot, it's nice and symmetric um, around the resonant frequency, and we have an extremely low standing wave ratio through the part of the 6-meter band that we want to operate. And you can see up here at 50.125 megahertz, our target frequency, our SWR is 1.06, which is extremely good. Next slide, we'll take a look at some other measurements that you can do with the antenna analyzer. Okay, so this plot up here in the top left-hand corner is the SWR plot that we just looked at. So on the last slide. Then we go here to the top right plot. We have a plot of the resistance, the reactance, and the magnitude of the impedance. You can see the green is the reactance, and through the 6-meter range that we are intending to operate, our impedance is almost zero. Right through here, you can see nice flat response here. Our resistance and our impedance are at the same value, about the same value. And the reason for that is the impedance is the reactance plus the resistance. And since the reactance is near zero, the resistance and the impedance are pretty much the same. And ideally, what you want to have in an antenna is for the impedance through this range to be at or near the impedance of your feed line, which is 50 ohms. And you can see we've got that. And what that does when you have your antenna impedance and your feed line impedance match, that's where you get your maximum power transfer. That's true whether it's an antenna or an amplifier. You want that impedance match there to get the best power transfer you can. And then as a result of that, if we look at the return loss is a measure of the amount of reflected power you get. You can see it should be very low because our SWR is very low. But at this point here that we're at the resonant frequency, our return loss is 30 dB, which means that you're getting about 99 to 99.9% of the power that you deliver to the antenna radiated from the antenna into the atmosphere. And that's exactly what you want to have, because that gets you the most power you can into your signal for the best propagation. And then finally, you take a look here at the phase, the voltage and current through the 6-meter part of the band we're going to use. And because the reactance is zero or nearly zero, we have almost zero phase angle through this range of the frequency spectrum. And that means that our voltage and current are pretty much in phase in the antenna. So all these indications, all 4 of them really point to an expectation that the antenna should perform extremely well on 6 meters and give us good power transfer and the best propagation we can get at the time. And that's about all I know at this point. So the plan is to go ahead and replace the A, B, C, and D elements with the 12-gauge wire and see where we go from there. Hope to have that done here in the next week or so. And so maybe before the next club meeting, I can issue a further update. So if you have any questions, concerns, or ideas, I'd be happy to hear them. Just drop me an email or give me a call, and I can talk about this stuff all day. So 73. This is K3SKS, and I'm clear.